Why is there a panda at that table in the corner?
We're not sure. Those ladies were just discussing data science frameworks, and next thing we know, there's a panda sitting there. He's friendly enough, though.
Excuse me, but I just found these snakes under our table.
Jess, we may have a problem.
I will go find the unicorn.
This season of the Bug Hunters Café is made possible by Softerific, Mousepaw Media, and Manning Publications.
Who's asking?
I just felt compelled to make small talk.
That's just because Alan K is at the next table over.
Snakes. Why does it always have to be snakes?
Oh, hi, Bojan. We have a bunch of Python developers in here today.
The Pythons are learning how to code now.
What? Oh, no, the humans are the Python developers, but it seems that every time they mention the language...
Another snake appears?
Usually. There are exceptions. John Cleese appeared out of the blue about 15 minutes ago.
So the birds overhead are...
Swifts.
Sounds like unicorns at work. It would also explain why our table is covered in rust.
I was wondering about that since we hadn't mentioned the language. Who's joining us today?
Lily Mara. She's an author of Refactoring to Rust, and she's a software manager at OneSignal.
I've been meaning to learn more about Rust, especially since it's being considered as an alternative to C.
Jason?
Don't worry, we've managed to contain the ocean in the janitor closet. We should be fine as long as no one goes for a mop. Oh, hey, Lily. We're over here.
Oh, hey guys. I was just trying to implement divide by zero support in the Rust compiler, and all of a sudden I showed up here.
Oh.
This is a lovely cafe you have.
Yeah, I didn't realize divide by zero could do that. Maybe that's why all the compilers are blocking it.
Yeah, it's scary. They want to keep us out of the Bug Hunters Cafe.
It's the bugs, they're conspiring.
They're conspiring against us, yes.
Clearly.
Well, Jason, I'll have my usual decaffeinated coffee with a touch of rainbows.
Alrighty. And Lily, what would you like to drink?
I'll have a double shot latte with some tears lost in the rain.
Okay, I can do that. I think they just got a fresh order of tears, too.
Oh, perfect.
Someone was trying to refactor something into COBOL from assembly, so...
That's a mistake.
Yeah. So, we have a lot of tears from that one. I'll go get that for you.
That's a perfect source. Perfect source. I would say you should just keep that in assembly.
I have a theory. In a million years, when mankind is gone, there's still going to be COBOL engineers around fixing stuff.
That's right. Did you hear the joke about the COBOL engineer who cryo-freezes himself to be woken up in 1,000 years? And they're supposed to be woken up in the year 3000. And finally they wake up and they say, "Oh, the year 3000. It must be beautiful here." And the person who woke them up says, "No, it's the year 2200, but you know COBOL."
A COBOL is an eternal love. It will never die.
Absolutely, absolutely.
By the way, I read your book and I absolutely loved it.
Thank you so much. Can I ask if there was any part in particular that stood out?
Well, for me, it was absolutely mind-blowing when you started talking about ownership and life cycles, because that was something completely new to me. And yet so logical when you think about it.
Yeah, have you done much C or C++ development previously?
Only during my university, so that probably be no.
Yeah, so the thing that's really interesting about Rust is a lot of the concepts that are in the language were actually not invented by Rust people at all. They're not necessarily new ideas. So the ownership system, the lifetime system. These are very common ways that professional C and C++ developers talk about their programs, but they're just things that haven't had support at the language level in those languages. I believe there may be some other languages where there are similar systems, but in C and C++, the language has no concept of ownership and lifetimes. But if you look at documentation for popular C and C++ crates, it's not unusual to see documentation comments for functions that say things like, this function takes ownership of the pointer you're passing to it, or this function is borrowing the pointer that you're passing to it. And so the neat thing about Rust is it just takes those concepts and it formalizes them into the language itself, and the compiler will prevent you from making mistakes with those semantics.
Here's your coffee, Bojan, and here is your downpour despair latte. Lily.
Thank you. Thank you. Delicious.
For me, it's always a big plus when compiler tells me something goes wrong. That usually means that the client is not going to call me in the middle of the night to tell me that something went wrong.
Absolutely. At OneSignal, we operate a lot of Rust code, and I'm generally not super nervous about doing large scale refactors on our Rust projects because the compiler is so good at just holding your hand and finding every spot in the code base where you need to update references or update types. Doing refactors is generally just a matter of, changing the one central place where something is referenced and then running the compiler down from, 200 errors to 0 errors. And you can be pretty confident that the thing that you're wound up with is going to work as expected. Versus, when we're making changes to our older Ruby on Rails code base, I'm begging and pleading to not be the one who's in charge of that because I'm just terrified that I'm not going to find every reference to something. It's really great having a compiler that can hold your hand.
Yeah, and there's one concept in Rust that I keep seeing more and more, and that's immutability.
Yeah.
By default, everything is immutable, and when I first came from Python with immutable stuff, I was like, why would somebody use immutable variables and objects? I mean, we always want to change stuff. Can you explain us why immutability is good for programming?
Yeah, absolutely. And I understand that the first time you look at the language and you see a variable binding that just says let x equals something. That is an immutable binding. X cannot be changed after that line. But I would maybe slightly argue with the idea that Rust is immutable by default and say that Rust has, well, okay, I suppose it is immutable by default, but I would more characterize it as optional mutability because I would say that most programmers would be pretty surprised by how often their variables can be and probably should be immutable. Writing a function in Rust is a very expression-oriented language. It's very built around building up a big expression that computes to a single value and then storing that in a variable and then using that to go to the next variable binding. The fact that the language has optional mutability means that the times when you do want to opt into mutability can be much less surprising. So let me give an example of that. So this is something that I also talked about in my recent conference talk at QCon London, but there are many libraries in Rust. Well, there are many libraries in many programming languages that you need to have a buffer of some data, you pass that buffer to a function, and that function will internally need to do some shuffling around of the data in the buffer. Maybe it needs to sort the data, maybe it just needs to swap a bunch of stuff around, maybe it needs to inject new data. And the way that a lot of programming languages will handle this is that function will actually make a defensive copy of your data buffer so that when you pass it to the function, you will not have your data changed out from under you because you won't want to surprise your users, right? But because Rust has this explicit optional mutability system, the way functions like that very often work in Rust is they actually take mutable references to the data buffer, and they'll actually shuffle the data around in place. And because it's like called out at the language level, at the type signature level of the function that says this thing, will and or may mutate your data out from under you, programmers are immediately aware that the function may change their data. And they know that, oh, if the order of the data in my buffer are actually important to me, then I need to make a defensive copy of these data. But if the order isn't that important to me, then I can just pass it to the function directly and deal with whatever order comes out in the end. So we're able to avoid a bunch of defensive copies by calling out where a mutation is going to happen and allowing developers to make explicit choices about it.
I find it interesting. It's an interesting balance because, like, my primary two languages are C++ with a heavy dose of C mixed in, and Python. And so I kind of oscillate between these two worlds of the computer trying to make the best decision for you, and usually getting it right, but not always. And then the computer not making any decision for you, and you having, or the language, I should say, not making the decision for you, but you having to understand all the implications of what's going on. And of course, both of those have disadvantages because Python or Java or other languages that are going to do it for you are going to go with the general case, which is never going to be the best case. And so you have, like you mentioned, all those unnecessary defensive copies, or else you wind up with unexpected side effects. Python lists are infamous for this. But then on the flip side, you have, like in C, where you have to know that this is potentially going to happen, and you have to anticipate it. So what you mentioned with Rust is really interesting because it ensures that it doesn't have the opacity of decision making that you see in Python, where you can't really do much about it. But it also does not have the, well, you're on your own attitude of C and C++. So it still puts the responsibility on the programmer, like with C++, but they have the opportunity to make the best decision for their particular use case. Would you say that's a fair assessment of Rust then?
Yeah, I would say that's a fair assessment. I would say Rust, generally speaking, empowers the developer a lot to make their own decision. There are plenty of guardrails, right? Rust has a very strong type system. Rust has the ownership system that we've talked about previously. But generally speaking, within those bounds, programmers do have a lot of flexibility with how they solve problems. You can write Rust code that, to a certain extent, opts out of the ownership and the lifetime system. You don't necessarily need to write Rust code that uses a bunch of lifetimes and passes, stack pointer references, instructs, and do a bunch of complicated stuff like that. You can write very performant Rust code that just copies a bunch of memory every time you need to share a reference to something. Like, it's not going to be as performant as Rust code that avoids all copies and just uses references everywhere. But, for beginning Rust programmers, or if you're just writing a very simple program where you're worried about the orders of magnitude performance improvement that you'll get over something like Python, and less so on the super fine tuning, then you'll probably be pretty happy with performance writing a very naive Rust implementation.
So it sounds to me like where with C++, there's a lot of undefined behavior. And I'm going to admit, I love debugging undefined behavior. It's my favorite thing to debug is undefined behavior.
Who isn't? Who doesn't love that?
I have had people question my mental sanity for that statement. But it sounds like with one of the other goals with Rust, then maybe this is why so many C programmers are excited about Rust, is the idea that we're training undefined behavior for compiler errors, putting more of that in the compiler. Does Rust have undefined behavior, or is it all just more like...
Absolutely, Rust has undefined behavior. It's very easy to trigger. Rust has an unsafe keyword that you can put on a function or on just a block of code, and this allows you to get into the area of manipulating raw pointers. which is, basically necessary for integrating with C or C++ code, using the CFFI, or there's also some, 100% Rust behavior that you need to use unsafe for. Most Rust programmers, at least Rust programmers who are writing, user space application level code, will not need to use unsafe, right? I think we do have unsafe in like 2 or 3 places in the one signal code base, and at this point they're all unnecessary. They were necessary at the time the code was written, but they're like raw FFI with OpenSSL libraries, and it's no longer necessary. Better bindings have been written. You can write lots and lots of great Rust code that has no need whatsoever for unsafe, but it is there if you do need to integrate with C, C++ code, if you need to manipulate raw pointers for some reason, and you can absolutely trigger undefined behavior. There's actually a function in the Rust standard library that I believe if you call it, basically immediately triggers undefined behavior, and the function was deprecated because and the deprecation notice says, this function is essentially impossible to use correctly. The function is called standard mem uninitialized, and it returns a value of type T that has not had any initialization logic run on it. So basically, if you write, if you have a struct called foo in C and you write, foo x, foo pointer x, and then you dereference that pointer, right, to get uninitialized memory. That's basically what that function does in Rust. Except Rust also has the constraint built into the language that it assumes that every value of any type is initialized to some valid value. So that the compiler always assumes that. The compiler has no allowances for uninitialized values.
Yeah, dereferencing uninitialized memory is always undefined in any however you do it. Yeah, let's why. I'm just trying to figure out why do I'm sure there was some reason.
Yeah, so I can tell you the reason. So if you're interoping with C code, and let's say, for example, you want to call a C function that's going to fill a buffer with like a gigabyte of memory, right? You have to allocate a gigabyte buffer, and then you want to call a C function that's going to write a gigabyte worth of data into that buffer. If you're using C, which allocator, standard library allocator function, would you use to allocate that buffer?
Right. Yeah, you would not want to pre-allocate it to something like 0 because then you'd be doing 2 writes.
Yeah, you would use malloc to avoid the zeroing out of that memory, but because of the way Rust's rules work in the compiler, you'd actually be required to zero out all of that memory so that every value in that buffer was a valid piece of data, a 0, or whatever type you were putting in there. And the uninitialized function allowed you to create uninitialized memory, so you could skip paying the price of initializing all of those values. But
now that's deprecated.
Now that has been deprecated, and there's actually the function has been replaced with a type called standard mem maybe uninit, and it's actually an enum type that shows this piece of memory is either an uninitialized value or it is an initialized value that holds something. And so they were actually able to build into the language the concept of uninitialized memory. So there's actually like a type that encapsulates the concept of uninitialized memory. And this is now the way that you do that thing. But I think you can still call the mem uninitialized function if you want to get undefined behavior as quickly as possible in Rust.
So I guess the idea is not to avoid undefined behavior, but to make it to where you literally just have to break the glass and get the undefined behavior. Like what you're getting yourself into instead of being surprised.
Yeah, and I mean, you can still get single line undefined behavior with the new thing, with maybe uninit. You could call like maybe uninit new, like the constructor, to get some uninitialized memory, and then dot, I think it's assume init or something like that. Because at a certain point, you have to take the pointer and you have to say, yes, I am a developer and I am very smart and I'm smarter than you, compiler, and I understand that this thing has been initialized, even though you can't see it. So you can just lie to the compiler if you really want some undefined behavior to debug. Uh,
I'm not that desperate.
sure. But yeah, the idea is not like we can completely eliminate undefined behavior. We can completely eliminate pointer operations. It's let's write as much code as possible where that is not a possibility. And let's draw a little box around the code where, undefined behavior or pointer operations or unsafe code might live. And we can, uphold all our invariants around that little box. And then we don't have to worry about rechecking all those invariants in every other place in the code base.
That makes sense.
Yeah. You do have to be careful though, because it is totally possible when you're using unsafe code to write safe code that breaks your unsafe code. So let me give a brief example. Yeah, you two are surprised, but many people are surprised when you tell them. But if you think about writing a vector struct, you know, the standard library vector struct has a lot of extra helpers in there. But let's think about writing a very, very simple vector struct, right? It has a pointer to a data buffer. It has a length, the number of elements that are stored inside of it, and it has a capacity, number of items that can be stored before we need to reallocate. So we can write a push function that adds things to the buffer. That is going to require some unsafe code because we're going to have to use pointer writes and maybe reallocate. We can write a get function that'll need some unsafe operations to pull things out. But theoretically, we could also write a set capacity method that overwrote the number stored in the capacity field. And it wouldn't necessarily actually have to, from a strictly like compiler perspective, it wouldn't have to reallocate the buffer. You could write a set capacity function that only changed the number. It just lied and said, oh yes, I have set the capacity to 10 million. I know it used to be 1, but now it's 10 million. And then the next time our push method was called, that unsafe code would see that the capacity was now 10 million, and it would, happily do 10 million pointer writes past the end of our data buffer, which actually only had one thing in it. So the set capacity method is totally safe code, but our unsafe code relies on assumptions about our unsafe code that we need to uphold. So unsafe is kind of to a certain extent, it's viral complexity. So when you introduce it, you need to not only verify the unsafe code itself, but you need to verify everything that's feeding into it, all the values variables that are being fed into it as well.
Right. So basically, you can't get undefined behavior in Rust. At least you shouldn't be able to get undefined behavior in Rust without unsafe in some capacity. But the introduction of unsafe can mean that even safe code can be involved in the undefined behavior manifesting.
That's true. Yes. And so that's why, generally speaking, when people do have unsafe code, they will write structs or they will write modules and they will try to isolate that unsafe code as much as possible and, do things like assertions on invariants to make sure that they're upheld to, whatever extent possible. Sometimes it's not. Sometimes you do just have to trust the values. But yeah, the fact that Rust allows us to draw these boxes and to say that this code is unsafe and needs extra eyes on it is very valuable, I think.
So what I'm learning from this is don't try to be smarter than compiler. You're gonna lose. At least in my case.
You are going to lose. And, for examples like the maybe uninit stuff and uninitialized memory, like how often is the performance optimization for that actually going to matter? there absolutely are times when it will matter. If you're writing an operating system or you're writing a kernel and, your function is getting called in a super tight loop, whatever. There are lots of cases where allocating and zeroing out a buffer, zeroing out a buffer is going to have a non-trivial cost that you care about paying. But for 99.59 of cases, that is not the case. Most of us are application level developers, or we're writing services, we're writing web services, whatever, and it's unnecessary to get to that level of optimization. You're opening the possibility to shoot yourself in the foot. And, most of us can stay writing safe Rust code 100% of the time and not even have to worry about unsafe. When you're using a type in Rust that uses unsafe internally, a lot of the standard library collections, you don't have to think about the fact that there's unsafe operations going on under the hood. You never have to call an unsafe method. You never have to do any pointer manipulation. It just looks like a type, and you can manipulate it, just like any other Rust type, or very similar ways that you can manipulate types in other languages. The fact that there's unsafe under the hood doesn't impact the experience of other developers, which is very nice.
So basically what I'm hearing then is that ultimately premature optimization is the root of all evil, as Stockbooth would say.
Yes, I definitely agree with that. But there's that quote is often shortened to that sentiment, but I think it is like a 2-sentence quote from that.
They optimized it. They optimized
the quote. Yeah, exactly. But the full context there is something like, in 99 or 97% of cases, premature optimization is the root of all evil. However, in those 3% of cases where it does matter, optimization shouldn't be discounted.
Yeah. Or I guess another way of putting that, I was just having a conversation at work where I was trying to solve something. It was a future feature and had a designer go, well, this is a future feature. We shouldn't bother with this right now. I said, it matters right now because I'm building a data model and I don't want to code us into a corner.
Yeah, absolutely. It's
leaving room for what you're trying to do, leaving room for the optimization, not excluding the possibility of optimization, while not implementing the optimization. That's a hard line to walk.
Right. But it's an important line to walk. Something that I do struggle with in Rust actually is because the language gives us so many levers that we can pull in the name of optimization and I don't know, getting to the best possible solution, and doing that in a maybe smart-brained but not necessarily scary or dangerous way, because the language has all these safeguards in place. It's very, very tempting to delve deep on a lot of these optimizations. When I'm reviewing PRs from folks on my team, I sometimes have the tendency to say, you could eliminate this copy if you wrote a bunch of extra code and propagated a bunch of lifetime arguments everywhere. But sometimes I fail, but often I try and stop myself from being too pedantic. But it's a problem where the language exposes too much and makes it too easy to do these kind of optimizations, to the extent that it's tempting us into acting on them. And I think about it in contrast with other languages like Python, for example. I'm always contrasting Rust and Python, and I worry that people are going to think that I dislike Python. I actually really like Python. It's just not very fast. If you're, going from something like Python to Rust, like I said before, the naive Rust is going to be tens to hundreds to thousands of times faster than naive Python. And then the micro optimizations that we do with reusing memory and lifetimes and all this stuff are just such minor, teeny tiny little changes, at the maybe single digit percentage level, as compared with the massive, massive speed up that we got just from going from a super dynamic interpreted language with a garbage collector to a statically typed compiled language that comes into machine code that has an optimizing compiler that has no garbage collector, like the performance gains are slightly out of perspective, I think.
Yeah.
If that makes any kind of sense.
It does. It does. And, performance around languages is always kind of interesting because it's so dependent on 1,000 things. Like, I've got a book coming out about Python, and one of the things I've mentioned is that, like, it's not that Python, and the funny thing is, it's not that Python itself is actually slow. It's actually that the default implementation of Python, the C implementation of Python, is slow. PyPy, which is actually a bootstrapped implementation off of our Python, it actually clocks almost as fast as C. But that has to be, that requires a lot of that engineering work. And I'd be curious to see what happens if anyone ever writes an implementation of Python in Rust.
Yeah, there is one. There
is
implementation called Rust Python.
Rust Python. Oh, yeah, I knew about that. What's wrong with me? I forgot. Yes.
Yeah, it is. It is out there. People are working on it. I don't know how active the development is. I'm not involved with the project at all, but I've definitely seen it and heard about it. People are tempted to rewrite everything in Rust, I'm afraid.
It turns out the unicorn crushed into a bookcase full of programming books.
So, how are we supposed to fix this?
He's trying to figure that out. Meanwhile, what's the special today?
Raspberry Pis. We had a lot of hardware enthusiasts come through earlier. Also, guests can get 35% off any order from Manning Publications at manning.com with the coupon code PODBUGHUNT21. These snakes are getting out of hand. Why couldn't this happen on a day when we had Ruby or Perl developers in here? Oh! You call 1988 Larry Wall. Tell him the coffee's on us today if he brings in his Perl development team. I'll call 1997 Yukihiro Matsumoto.
On it.
So, something you mentioned, something we were talking about a minute ago. Everybody seems to want to rewrite everything in Rust. Like, let's rewrite all the C code in Rust. Let's rewrite the kernel in Rust. Let's that's a big thing right now. Like, rewrite the entire Linux kernel in Rust and all these projects to rewrite. What's your take on that? Is Rust the new C?
So, Rust certainly has a lot of overlap with C, right? It targets basically the same performance area. It allows developers to write really low-level code, but it's significantly more expressive than C. It has a lot more guardrails than C. So it's very, I think, tempting to want to rewrite everything in Rust. It's something that I think I was, if not advocating for, at least like silently hoping for towards the beginning of my Rust programming career. But I think working in industry a little bit longer gave me some more perspective on that. And I think it's a little bit, presumptuous to think that we can just rewrite all of the C code in Rust. And I don't know, maybe for these really large scale open source projects like the Linux kernel or whatever, they're starting to add in, at least from my understanding, I'm not super involved with the efforts there, but actually I'm not involved at all. I don't know why I said that. They're starting to add in Rust, not as a candidate for rewriting the kernel, but as a sort of an additional language choice that developers have when they're writing new kernel modules. So this is an approach that I talk about a bit in my book, which is called Refactoring to Rust. So it's sort of a response to the idea that we should rewrite everything in Rust. Doing full rewrite projects is risky. They're always running behind schedule. They're always going over budget, introducing new bugs, and they often don't fix like underlying architectural problems. Like if you're rewriting a single service, in a larger system because, you're just making changes to the one service, not necessarily the larger system. But it's an option that we have because Rust has such like a nice, easy way to interop with C code. It's an option that we have to take an existing program and sort of bolt some Rust onto it and communicate from a Rust library to an application written in some other language using CFFI. So there's language level support for the CFFI, and then there are binding libraries available for C++, for Python, for Ruby. Those are certainly the most popular ones. Oh, Lua, Node.js. Many, many languages have binding libraries available for Rust that allow you to take a Rust library and expose a wrapper library in some other language. And then developers in that other language can call functions that underneath are Rust functions, but to the developers in that language look no different from functions written in the host language. So this is something like I just recently spoke at QCon London about doing this thing as well, like taking a function that computes some statistics in Python and writing that same function in Rust and then calling across the FFI boundary from Python to Rust. And I believe that function was either 1,000 times or 10,000 times faster than the pure Python implementation. And this was being benchmarked from the Python side, with paying the cost of doing the FFI and the data transformations and whatever. So that I think was a pretty fair micro benchmark of that function. Like there are really, really significant performance gains that are to be had from going from something like Python, Ruby, Node into Rust. And, via profiling, via flame graphing, via tracing, whatever, we can identify the components of our system that are the most performance intensive, that have the highest CPU cost, and take those pieces, re-implement those pieces in Rust, and then call from a slower language that most of our application logic is written in into a faster language like Rust. And that's basically what my book is about, how to do that.
Well, tell us more about that. Do you usually start refactoring the CPU intensive parts, or is there another way to start with the refactoring process?
So, it depends on what your goals are, right? So it might be the case that your goal actually is to re-implement your entire service in Rust. If that's the case, then, maybe you would start with the most CPU intensive code, but you might also decide you want to start with the simplest code, right? What is your simplest endpoint? Reduce the number of variables that are changing at one time and re-implement that in Rust. And then, call over the FFI boundary to that. You might want to start with the most CPU intensive thing, but you might also want to start with the thing that's going to be easiest for you to implement and easiest for you to debug and raise the fewest questions when you do it. Most CPU intensive may also likely be most complicated, right? And maybe you do or maybe you don't want to start there, depending on what the goals are for your project. If your goal is just explicitly like, we have this one endpoint or, part of the execution of this one endpoint that's 90% of our CPU time is spent in there, then yeah, maybe go for doing that one first. If you have a bunch of Python developers and they're writing Python and they love Python, but there's one place in the code base where the Python performance is really getting dogged, then, maybe explore using Rust in that one place. But, there's no reason that you have to tell everybody to stop writing Python because you have one place where performance is bad.
Usually, when I get to that point, I just buy coffee of ice cream and go and beg C++ developers to rewrite the function. So far, it worked pretty much nicely.
Yeah, the thing that's nice about Rust is it empowers developers who don't necessarily have a lot of experience writing low-level code to write code that is very fast, very performant, my book is targeting people who have experience in some programming language, not necessarily C or C++, but, Python or Ruby or JavaScript or whatever. Like if you have experience with some kind of imperative programming language, you're gonna be able to write Rust code. It's the goal of the language. I think the headline of the language on the website is empowering everyone to write. I don't remember how it is, but I know it starts with, empowering everyone. The point is that we want people who weren't necessarily able to, or maybe were able to, but felt scared off, felt like they weren't able to write this kind of really performant code because they were scared off by C or C++, to be able to do so by handing them Rust.
A language empowering everyone to build reliable and efficient software.
Yeah. Okay.
Well, and it's interesting because then it sounds like you're actually introducing a bit of a paradigm shift on top of a paradigm shift. Like Rust sounds like it is itself, in a way, a paradigm shift from a technical standpoint. It's like here's the control of C with the safety rails of something higher level. But the paradigm shift that you seem to be introducing is the idea that we're not marrying the language. I think a lot of times we tend to feel almost like we're entering into a long-term commitment with the language, until death do us part. That, I'm committing to learning and mastering this language, and I'm going to write everything in this language. And your book kind of seems to be coming from the perspective of a language is just another tool in the tool set. And if getting the job done involves bringing in some other tools for this specific thing, that you can do that.
Yeah, absolutely. Absolutely. And somebody recently asked me about, how, is Rust a systems programming language? Or what is a systems programming language? And I feel like we were constrained on this term for a long time. Like when Rust first came around, it was definitely classified as a systems programming language, And I think that term sort of scared people off, because when they heard systems programming language, they thought of something with manual memory management that was scary, like C or C++, and they were like, oh, that's not for me. But the reality is that Rust has such good guardrails in place, it has such high-level semantics in the language, that there's no reason that we can't write, high-level application business logic code in Rust that, you would be probably derided pretty heavily for suggesting writing in C or C++. So I think the term, systems language or terms like it are very constraining when you have a language that's as flexible as Rust.
Well, they're weasel words, just like scripting language. It doesn't really mean anything.
Exactly.
Referring to the most common usage, but not necessarily the... Well, and you mentioned a moment ago that delineation about, well, Rust is one of those languages that is, assembled down to machine code. And it's funny how we have to kind of tiptoe around this, because we have this, we can't say compiled language anymore, because it's like, if you say compiled language, then you have the Java crowd go, well, we're a compiled language.
Right.
And then by their semantics, so is JavaScript and Python. It's like, well, it's compiled to something, but I actually wanted to point in the term assembled language because I got sick of the debate. And it's just like, okay, we have interpreted languages and we have assembled languages. Interpreted means that it does not become machine code until it lands on the end user's machine. And however, whatever the timing is on that. And then assembled would be that it is invariably turned into machine code on the developer's machine, or on a build system before it touches the end user's computer.
Right.
That seems to be a more useful delineation, but I digress.
Yeah, that's interesting. I've definitely been part of conversations with arguing about what is and isn't a compiled language. And I don't know, there are so many dichotomies in software that are just wholly unproductive and exist just to, I don't know, make people feel smart when they win arguments.
Language is insidious.
Yes.
So changing gears a little bit, what are the strangest bugs you've ever run into?
Yeah, absolutely. This is a bug that didn't start out very strange, but when we finally uncovered the root cause, it was extremely strange. So, at my company at One Signal, we use Kafka very heavily. Many of our operations are done using asynchronous Kafka consumers. My team is the team that operates these consumers, and we use it for a variety of reasons. We use it for analytics roll-up jobs. We use it for event-driven systems. And we also use it in the capacity I'm going to be talking about now for queuing Postgres writes, because we're underlined by Postgres, and occasionally we get into situations where we're constrained on Postgres performance and we need to delay writes for some reason without we don't necessarily want to cut off our API traffic when that's happening. So one of our Kafka consumers is something that's responsible for writing updates to our subscriber model into Postgres. So you call our API, our edit device API, and you change the tag from, favorite color from blue to green so that you can start, offering your customers sales on green shirts instead of blue shirts. And this API call completes very, very quickly because all it's doing is a Kafka enqueue. And then at some point in the future, we will take that update and we will persist it into Postgres. It's an eventually consistent API, and it fills the needs of our customers pretty well. Occasionally, we would get into a situation where the latency, which is the difference between the latest message in-queued and the latest message that was dequeued and processed and committed, that latency would grow very, very large. And I think 10 to 20 million messages in latency would show up, and we kind of didn't understand why. We would get into situations where, and this is something that was kind of bugging us for a while. It was even before the pandemic, so we would have like 5 or 10 developers huddled around, a single computer, like staring at graphs, looking at Kafka logs, trying to figure out what the heck is going on here. We couldn't figure it out. So, of course, we start adding some more instrumentation, right? And we figure out that the latency is pretty much isolated to a small range of partitions. And in Kafka, the data model is basically a topic is like a logical group of messages. So, sorry, for those unaware, Kafka is a distributed message queuing system, sort of similar to, I think, RabbitMQ, but it's basically just a giant distributed queue. So you in-queue messages on one side, you dequeue messages on the other side. And then as a part of the dequeuing process, like you can also send Kafka commits that acknowledge, like, yes, as a consumer, I have dequeued and processed this message. It's done. Don't give it to me again. So we have topics, which are logical groupings of a bunch of messages in a queue. And within a topic, that is subdivided into numerical partitions, which are basically the way Kafka handles concurrency. So if you have a topic that has a bunch of messages on it, you probably can't process all those messages with a single consumer instance. You maybe want to have, 10 or 100 consumer instances. And the way you do that is by assigning each of those consumers a range of partitions on the topic. And partitioning can either be done randomly by Kafka itself, or you can explicitly have partitioning logic in your producers and your consumers. We use explicit partitioning logic, and the way that this particular topic was partitioned was based on a combination of the subscriber ID and the customer ID. It was like a mix of those two. And so we were seeing this latency appear sort of smeared across a range of partitions. And at a certain point, we began to theorize that there was, one particular app, one particular customer that was maybe causing this latency. But once again, we couldn't really figure out what exactly the cause of this latency was. We couldn't find malformed data in the messages. We couldn't find like super, super giant updates in the messages that would be causing them to process slower or anything like that. And so, once again, as always, we added more monitoring. We add some more monitoring, and we discover that our concurrency is actually being impacted. So, in addition to this partition level sharding of a Kafka topic, inside of our Kafka consumers, we also have subpartition concurrency. And I think in some circles, this is not really recommended, but we kind of need to do it because of the scale that our consumers are operating at. And so we are taking each Kafka message, computing some kind of hash on it that's based on, I think that is based on just the subscriber ID, and using that hash to assign it to a particular worker. And we discovered at some point that the number of workers that were actively processing messages when we got into this really bad latency state actually dropped down to 1.
Oh.
Yeah, down from, I think like 256 was probably what we had previously. And so we discovered that instead of doing, 256 things at once, our consumer was only doing one thing at once. We're like, well, that's certainly going to have a pretty significant impact on its throughput if we're cutting off so much of the concurrency capacity. But why might it be doing this?
So if I'm following you so far, then basically the sharding that was happening on the upper level was somewhat covering up, some concealing the fact that on a lower level that you were dropping down to 1 work.
Basically, yeah. So, if we were doing, I guess, random partitioning at the higher level, we may have seen this behavior, across our entire fleet, across all partitions and all workers. But because we were doing the higher level explicit partitioning, it was isolated to just a single worker, to just that one worker's range of partition. Excuse me. And it was always coming back to this one worker. It wasn't, well, not one worker node, but one logical worker with the same range of partitions. It was never shifting around. So we were once again suspicious, highly suspicious, that there was a single thing that was causing this, and we couldn't figure out why. At a certain point, we decided that the issue had been going on for long enough, and I don't mean like one isolated incident where we got into the lag state. I mean like this lag state thing had come and gone so many times that we're like, all right, we need to actually like consider spending some money on fixing this problem, right? So we spun up some structured logging, and we started doing some sampled structured logging of basically every event that was being processed by this consumer into Datadog. And yeah, it's going to cost us some money to shove the data up there, but this has been going on for too long. We don't care. We're going to pay it. We're going to fix it. We're going to figure it out. So what we discovered was very interesting. We discovered that when we got into this state, the worker instances that were lagging, that had their throughput dog, that only had one worker running, were mostly processing updates for a single subscription. Yes, a single device that was operated by one of our customers. And we wondered, why is this one device getting so many updates? And we looked at the updates. We looked at the content of the updates. We're like, these updates don't make any logical sense whatsoever, because they were just thrashing fields. They were just constantly changing fields, like the same exact field from one thing to another. They might say, set their country to Australia, and then 100 milliseconds later, set the country to Mexico. Just nonstop. Every single field for this one device was being thrashed. And, not only was that bad because we were obviously processing a bunch of garbage data, but because these updates were eventually going into Postgres, like Postgres wasn't really happy about a bunch of writes going to the same exact row nonstop. Like if you operated Postgres before, you'll know that it's not a really big fan of having one row constantly slammed with updates.
Yeah, with the country changing that fast, Dr. Gordon Freeman, I presume.
Yeah. So I think we did like put some code in to just like disable updates to this one subscription. Like if you see an update for this one subscription, just drop it. Don't try and send it to Postgres. Just drop it. But then we thought like, okay, why was this happening? Why is this one device getting slammed with so many updates? So we took a look at the fields on this one device, and we noticed that like every field was being updated, but there was one field that wasn't being updated, and this was the email field. So as a part of OneSignal's product offering in our SDKs, we have an SDK method called setEmail, and what this does is if you call setEmail with say LilyMara at onesignal.com in our SDKs, it will send up an API request. It will search your user base, your subscriber list, and see, hey, do we know anything about a user with the email LilyMara at onesignal.com? If we do, then it will create a link between this like device level push notification subscription and this email subscription, so that the two will be linked. And this is the very important piece, so that when you make updates to the push device, those updates will be copied onto the email device, so that you could do things like if you want to target people via email, you can use the same like data tags and fields for targeting email people as you use for targeting push people, because the tags are like copied from the push record to the email record. So what we found is that one of our larger customers had called this setEmail method on their 5 or 10 million push devices with the same email address, with something like admin@mycompany.com.
Oh, man.
Yeah. And so, as a result of this, every time any one of their 5 or 10 million subscribers had any field updated, it created a duplicate update sent to this one central subscription. And
Man, so it was hammering it because every single device with this email attached to it was trying to update the correct information, and they were basically just, the term that comes into mind is wrong, but it's Z fighting. It's what comes. It's data fighting.
yeah. So, like, from a number of updates perspective, like, it's nothing. It's a rounding error. But it violated so many assumptions that were at the core of our system. It violated the assumption that, oh, there's never going to be a bunch of writes to a single device, because, the writes are going to be very well distributed across a customer's range of devices. But we didn't account for this email linking feature that allowed you to duplicate writes very, very easily to a single central device if you were so inclined. Yeah, so that was a really interesting one and a very hard one to debug. And I definitely did not solve that one alone. And as a matter of fact, I was not even leading the effort on solving this bug, but I played a part in adding the structured logging and identifying the cause and trying to steer the investigation in the right direction. But the folks on my team really led on that one. But yeah, that was a real head scratcher for a very long time. And when we finally discovered what it was, there was such an enormous face palming from everybody who knew anything about the bug.
I think that's one of my favorite bug stories to date, because like you're going through it and you're thinking, I don't, especially because I was sitting here going, I've never used Kafka, I've used Postgres, but I understand this part, I don't understand that part, and I'm just like catching these little pieces, and I'm thinking, I wouldn't know where to begin, and then when you say the solution, it's like, oh my god, it almost hurts. It's like,
It does.
It should be obvious, but yeah, it's layers of abstraction and unstated assumptions cover up so many things.
They do. Yeah, that's It's one of my favorite bug. Well, no, it's my favorite bug story too, of course, because I just shared it on a podcast about bugs. But yeah, I love it because it, like you said, it has all these layers of assumptions, and that's really what bugs are, right? Bugs are not computers making a mistake. Bugs are a collection of assumptions that developers make about the world being invalidated.
Yeah. Bugs are collections of erroneous assumptions. Yeah.
Absolutely.
I think Vitahe last year mentioned pretty much the same thing, that all bugs are wrong assumptions.
Yeah, or just typos, I guess. But those are much less interesting to talk about.
Yeah. And then use Rust to find them.
Yes, exactly. I think it's very difficult to have a typo related bug in Rust that isn't just, well, I mean, if you had variables that were one character off from each other, I suppose you could return the wrong one or something like that. Or, of course, you could have a bug that's just, presentation logic, show the wrong string to the user. But it's not like JavaScript or something else where you're actually going to have a production-facing bug that's the result of missing a semicolon or something like that.
Had those.
And Rust actually does have significant semicolons, which is interesting. People are very often surprised and a little bit incredulous when I tell them that. But it does have significant semicolons, but the compiler will not let you get away with making a mistake on those.
Which is probably a mercy more than anything.
Yes.
This has been a wonderful conversation.
Thank you.
I don't think I've ever not enjoyed a conversation in the cafe, but I feel like I know so much more about Rust now than I did at the start of the conversation. And it's got me thinking about, where is this tool useful? Because I will admit I was resistant to the idea of using Rust, because it's like, well, I'm using languages that work. I don't want to rewrite everything. That's what I kept hearing, this whole idea of don't refactor necessarily everything, but find where it's useful to use it. And I like that. I think I'm going to be looking for more opportunities to do that.
Yeah, excellent. Well, I've had a great time coming here to the cafe and speaking with the two of you today and talking about Rust. I'd be happy to come back anytime and talk about it more.
Best divide by zero you ever did, huh?
Best one yet. I'll have to come up with some other impossibility to try the next time I'm thirsty for some tears lost in the rain.
Oh, you've been an absolutely wonderful guest.
Thank you. Thank you.
And now I got to see if we can get some of this Rust off the table, because it's pretty well encased by this point.
I guess you'll have to find something else to talk about when I'm gone.
Absolutely. Some sort of, I wonder if they named a language after a solvent. That would be helpful.
Or marble or porcelain, something nice like that.
Yeah. Stuff to ponder.
Bug Hunters Cafe, this is Jess. Yes, we're still open 24/7 at bughunters.cafe. You can also find us on Twitter as Bug Hunters Cafe. Oh yes, music is provided by audionautics.com. We have a link on our website. We have an awesome giveaway. You can win a copy of Refactoring in Rust by Really Mora. For your chance to win, just retweet our Twitter post about it and then follow Bug Hunters Cafe for the announcement of the winner in a few weeks. Sure, you can bring in your team. Out of curiosity, what language do you work in? Java? That will be handy. Oh, never mind. Yes, come on in. We will see you soon. Bye-bye.
Well, so much for that plan.
What's wrong?
As soon as the Perl and Ruby development team sat down, the unicorn fixed the problem.
So we had to deal with snakes, rusting metal, and misplaced oceans all day. And then as soon as we find a way to turn it around, then it stops?
On the upside, no one mentioned the Dart language.